pleased to introduce the speaker for this session, Tim Costa. Tim leads the HPC Software Product team at NVIDIA. Previously, Tim worked as a performance library architect and HPC application engineer and owned enabling efforts for computational fluid dynamics applications at Intel. Tim obtained his Ph.D. in mathematics from Oregon State University on the development and analysis of numerical methods for fluid flow in stochastic or evolving porous media. It will now be our pleasure to hear from Tim Costa.
Thanks for listening in. I'm Tim Costa, Director of HPC and Quantum Computing Product at NVIDIA, and I'd like to talk a bit today about some of the latest innovations from NVIDIA in HPC software that are aimed at accelerating time to science. Today's grand challenges require simulation to occur at unprecedented scales, effectively leveraging complex heterogeneous architectures. Simultaneously, domain scientists are focused on reducing time to science rather than on increasingly complex computer science. Enabling developers to address these challenges with velocity requires a comprehensive and innovative software ecosystem of libraries, tools, frameworks, and applications. While I can't give comprehensive coverage of NVIDIA's efforts in HPC software in 20 minutes, today I'll review recent developments along 3 initiatives that are aimed at accelerating scientific discovery with HPC software innovation. Efforts around seamless acceleration, the creation of data center scale libraries, as well as the domain-specific focus on quantum computing. Enabling developers to focus on science starts with an investment in accelerated libraries, from core algorithms to linear algebra, signal processing, communication, and much more. NVIDIA libraries provide a foundation upon which scientists can build applications that get the best performance from the accelerated data center, all while transcending hardware generations and provided through drop-in ease of use. The scope of NVIDIA libraries also continues to grow, with new libraries that enable novel compute applications and groundbreaking features like multi-node, multi-GPU support. That said, if a library API doesn't exist for a use case, we need to talk about programming models. Over the past 20 years, NVIDIA's investments in enabling scientists has transformed the field of programming languages. The launch of CUDA in 2007 ushered in a revolution in accessibility of accelerated computing. The community effort to define the first directive-based model for accelerated computing, portable to multi-core CPUs with OpenACC, further expanded the group of scientists whose work could benefit. And in 2020, we announced another breakthrough with the support of standard languages running on GPUs natively with the NVIDIA HPC SDK. C++, Fortran, and Python developers can now write parallel-first code directly in their language of choice and benefit automatically from GPU acceleration. Before digging in on some of the exciting features in these areas, I want to introduce the NVIDIA HPC SDK. The HPC SDK is a comprehensive suite of compilers, libraries, tools for building HPC applications for accelerated supercomputing. It supports all the programming models described in the previous slide, including standard language parallelism, and it includes libraries for core algorithms, linear algebra, and signal processing, communication for programming the network, as well as developer tools for performance analysis and debugging. The HPC SDK is freely available and supports developers on CPU-only systems as well as GPU-accelerated systems. It's available through developer.nvidia.com. It's available as an MGC container, via SPAC, and is on all major clouds. Now let's dive into a discussion on standard language parallelism. LULASH is a shock hydrodynamics app out of Lawrence Livermore National Laboratory and is designed to evaluate performance with compilers and programming models for on-node parallelism. There are many implementations of LULASH using different programming models, including OpenMP, OpenACC, CUDA, MPI, and also standard C++ parallelism using no additional programming model. Here we're looking at the performance of LULASH with 3 different compilers and 2 different implementations, OpenMP and STUDPAR C++, normalized against the performance of our compiler MVC++ and the OpenMP implementation using all the available cores of a powerful multi-core CPU system. As you can see, OpenMP multi-core performance is fairly similar between the 3 compilers. As we move to the right, we see that the standard C++ implementation, with no additional directives or language extensions, actually gives us a 2 to 3x speedup over the OpenMP implementation still on the multi-core CPUs. What's more, the same code, with 0 changes to the source, can be used to target NVIDIA H100 GPUs, getting a 19x speedup over the OpenMP baseline running on CPUs. The roadmap for STDPAR, or Standard Language Parallelism, is rich. Let's take a quick look at this for STDPAR C++. Today, the C++ standard parallel algorithms already allow us to achieve the portability across different implementations and performance across both CPU and GPU that we just saw with the Lulesh example on the previous slide. However, the parallel algorithms are not the only feature of the C++ standard that is relevant to HPC applications and developers. To begin with, there was groundwork needed to enable the parallel algorithms, going all the way back to the C++ 11 standard. Things like clarifications of the memory model and extensions to atomics allow reasoning about parallelism, and clarifications and generalization of lambdas provided the necessary language machinery that make the parallel algorithms more expressive with user-provided operations. Then in C++ 17, the parallel algorithms were introduced. This is the main feature being leveraged by Lulesh, as well as the many other applications which have already adopted STDPAR as their method of parallel and accelerated computing. Since then, we have gotten more tools for parallel application developers, such as ranges and synchronization primitives. And there is much more to come in C++ 23 next year, as well as work already underway for future C++ standards. For C++ 23, NVSpan will allow HPC developers to better express multidimensional data structures, and extended floating point types will give reduced and mixed precision code even better support in the standard. But perhaps the most exciting new feature since the parallel algorithms will be senders and receivers, which will allow for asynchronous execution of the parallel algorithms. Using this new facility, developers will be able to express their parallel work as graphs, and then target that work to a variety of execution resources, including not only CPUs and GPUs, but also scale out to entire clusters of complex compute nodes. And here is a great example of the advantages of this new scalable model for asynchrony in the C++ standard and how it can bring benefit to HPC applications. Palabos is a production application from the University of Geneva for lattice Boltzmann calculations. This plot shows strong scaling out to 512 A100 GPUs, with the realized performance shown in orange coming very close to the ideal strong scaling. This result was achieved using only current features of the ISO standard for C++, with the addition of features that are already being discussed in the ISO C++ committee. No other language extensions or programming model for the GPU, for the node, or for multi-node communication were used in this result. These are exciting developments in the standard ISO languages. Many applications have already seen success by moving their parallel computation away from secondary programming models into the base language, whether it is ISO C++ or ISO Fortran. And you may have seen papers published about some of the applications shown below. NVIDIA offers a wide range of GPU-accelerated libraries. While I can't cover everything we're doing in libraries, I'll highlight a few areas of focus and some recent results. Libraries offer developers seamless acceleration with the latest NVIDIA systems, such as the new Hopper architecture and the Grace Hopper superchip, with little to no effort. To enable scientists to address grand challenges requiring supercomputing scale computation, we are extending our libraries by offering multi-node, multi-GPU functionality. The NVIDIA platform is an open platform, and developers can attack it from all levels of the stack. For those trying to squeeze the last few flops of performance from their kernel development, they can take advantage of our new device extensions. These extensions allow users to perform numerical operations within a CUDA kernel and have more control over data movement. Having the ability to scale out your application can enable scientific breakthroughs that were unobtainable in the past. As an example, computational fluid dynamics applications that study turbulent flow may be required to compute very large 3D FFTs in order to simulate high Reynolds number flows. The plot above is showing the throughput for 3D FFTs for a single iteration from a turbulent simulation. Each bar is the throughput for a particular problem size and the number of GPUs used during the run. Calculations in the iterations can be performed very quickly, making it possible to simulate high Reynolds number flows in a reasonable time frame. Our math libraries now offer dense linear algebra and FFT with multi-node, multi-GPU functionality, with the ability to scale to thousands of GPUs. NVIDIA also offers multi-GPU functionality for BLAS3, solvers, and tensor contractions. With the new math library device extensions, developers can now execute numerical operations such as FFTs directly within a CUDA kernel. Historically, these operations would be launched independently from host code. Depending on your workflow, this can limit performance due to additional data movement to and from global memory. Here is an example of convolution with FFTs. something you will see quite often in signal processing. For a simple workflow, you can apply an FFT to some input data, perform a custom operation such as scaling, and then perform an inverse FFT. In the plot on the right, we are comparing the throughputs of the classic FFT and new device extensions for different 1D FFT sizes. Depending on your problem size, you can achieve over a 2x end-to-end performance improvement. As one might imagine, performance gains can continue increasing as more operations are fused inside of the kernel. Quantum computing is a fundamentally new model of computing with many unique challenges and opportunities to impact a broad range of applications. The progress made by the community over the past decade has been impressive, from 1 to 2 qubit devices at institutes of higher education a decade ago, to systems with tens to hundreds of qubits available for general users in public clouds today. This is remarkable progress. However, to get to the point of useful quantum computing, there remains tremendous work to do. On the hardware side, quantum processor builders need to continue improving qubit scale and fidelity. Just as important is the work to be done in software applications and algorithms. With improved classical quantum integration and innovation in algorithms and applications, the scale and fidelity required for useful quantum computing can be reduced. To meet that challenge, governments, institutes for higher education and research, as well as industry, are investing heavily across the board in hardware, software, and algorithm development. GPU supercomputing is essential for quantum computing in 2 areas. The first is quantum circuit simulation. With quantum circuit simulation on the NVIDIA platform, researchers can develop algorithms at the scale of valuable quantum computing long before the hardware is ready. On the NVIDIA platform, we're already simulating quantum algorithms with tens to thousands of perfect qubits, representing the future state of fault-tolerant quantum computing. This enables scientists to explore use cases that may benefit from quantum acceleration, as well as enables hardware builders to validate and design future iterations of quantum processors. The second area where GPU supercomputing is essential is hybrid quantum classical computing. As we move past basic algorithm R&D to work on building full quantum applications with tight classical quantum integration, a platform for hybrid quantum classical computing with emulated quantum resources is an essential research platform. Long-term, all useful applications of quantum computing will be hybrid, with quantum computers acting as an accelerator for key kernels alongside GPU supercomputing. In 2021, we introduced cuQuantum, an SDK for accelerating quantum circuit simulation. cuQuantum is built to accelerate all circuit simulation frameworks, and is integrated into Cirq, Qiskit, PennyLane, Bracket, Exact, Orchestra, Kibo, and more. With cuQuantum, researchers can simulate ideal or noisy qubits with a scale and performance not possible on today's quantum hardware or with unaccelerated simulators. The cuQuantum appliance is a ready-to-deploy container consisting of leading community frameworks accelerated by cuQuantum and optimized for the NVIDIA platform. On the bottom of this slide, I've included the performance chart I showed at the last 2 GTCs ago for the cuQuantum appliance. We were very proud of these numbers in the spring, and I'd say as we should be. We saw great strong scaling with performance on a DGX providing up to 90x speedup over alternative systems. However, we're always looking for more performance. This often comes through software updates on the very same systems. If we compare the results in the spring to the results now, we see up to 4.4 better performance through a software-only update to the latest cuQuantum appliance. This means that quantum research groups that are using the NVIDIA platform see their simulation solution increase in its capability over its lifetime, at times dramatically, through software innovation. cuQuantum has been adopted by a broad range of groups spanning the entire quantum ecosystem, including supercomputing centers, academic groups, quantum startups, industrial end users, and some of the largest companies in the world. BMW is leveraging cuQuantum to optimize pathfinding and routing for robots. Large consultancies like Deloitte and SoftServe are developing applications in quantum machine learning for both materials and drug discovery to address their customers' most pressing problems. Fujifilm is leveraging cuQuantum to explore tensor network methods for material science simulation with thousands of qubits. In order to enable scientists to address the grand challenges facing our society, innovation is required across the full computing stack. Today, we discuss some of the ways NVIDIA is investing and innovating in HPC software, enabling scientists to focus on science by enabling seamless acceleration on advanced architectures, by enabling data center scale computing with multi-node, multi-GPU libraries, and by providing groundbreaking scale and performance for specific scientific domains, with a focus today on quantum computing. Thanks for listening in, and have a great conference.
soon.